All right, let's get crazy. I'm Ray Myers. Welcome to Craft versus Cruft with another refactoring challenge. And this is, as the count goes, number three. Number zero was the infamous spinning 3D donut as implemented in this donut shaped obfuscated C code originally by Andy Sloan. And in spirit of that, I'd like to do something of a similar tradition. I'm even going to dial up the difficulty a little bit as you'll see. This will also be an obfuscated C challenge, but we're going to pick something that was actually a winner of the International Obfuscated C Code Contest, which, if you're not familiar with, is exactly what it sounds like, and it's been going on for quite a while now. It's been going on since the mid '80s, actually, and these are tough. I've tried a few of these. I had a lot of luck with Andy Sloan's donut. I thought, okay, maybe I can finally untangle some of these, because if you ever looked at one of these obfuscated C code winners, it's kind of mind-boggling to contemplate how they're doing what they actually do. But I quickly ran into the wall because these are very difficult. These people are very good at writing very unreadable code. But nonetheless, we're going to try today to start to do that to one of these. And this is going to be a multi-part. We're not going to get all the way through, but hopefully in each segment, we're going to illustrate some useful principles and get some meaningful step closer to the destination. So couple things to make clear here. While these are more extreme examples than you're likely to encounter in the wild, we are going to be using just the same refactoring techniques, the same ways of extracting insight from code and better expressing them in it little by little, with a working example at every step. So we're going to be using the same techniques, just with a little more discipline and creativity. And also, I'm not a C expert, right? I did some C in college. That was a long time ago. I've used mostly other languages in my professional career. So it may look to you as though I really know what I'm doing, but in C land, I'm really more of a novice, and I'm more applying my general programming knowledge and refactoring techniques to this. So even in a situation where you don't know the language that well, and where you don't know the code base at all, and you don't have access to the person who wrote the code base, this kind of demonstrates that these refactoring techniques are by your side and will help you. So let's go all the way back to 1986, and one that jumped out at me, which was actually 1989. Let's go to 1989. And jar 2, they're named after the submitter, and this was the second one they submitted, I believe. This is a Lisp interpreter. So if you're familiar with the programming language Lisp, this actually implements an entire additional programming language, a pretty serviceable programming language considering all things here, in just this small amount of code. Now, Lisp interpreters are, notoriously very simple to write relative to other languages because of the very clean syntax and kind of economy of concepts that you see in that language. But, this is even shrunk down relative to what we'd expect there, and of course, completely unreadable. Let's see what we can do here. So let's first look at, if you go into the site, and they each come with a hint file explaining what this thing actually does, and some comments from the writers and judges. I'll be using CLion, which I installed just for this, which is the C IDE that JetBrains puts out. They've got one, like in IntelliJ IDEA. They've got all these different ones. Some people use PyCharm and WebStorm, all in the same family. Their one for C is called CLion. And I've brought in the code base, and I've also brought in, as the Readme, their hint file. The judges have noted the most useful program entered this year, a rather large subset of Lisp. They've talked some limitations, but all this functionality in such a small program, impressive enough. They gave this the Best in Show award for 1989. And then the authors noted which particular Lisp primitives that you need. It's not very many, but you can do a lot with little in Lisp. And then they've given examples of these are some inputs and outputs. So you can define a Fibonacci program. If you're not familiar with Lisp syntax, this may look a little strange to you, but this is how a normal Lisp program actually looks. This is, you know, a pretty normal behaving Lisp dialect, and they're defining this Fibonacci function and saying, you know, if n is less than 2, return 1, otherwise return the sum of Fibonacci of n minus 2 and n minus 1. It's might be confusing to you if you haven't used Lisp, like what's going on with this minus n2 when I say n minus 2, and that's because they're using prefix notation instead of algebraic notation to express function application, which means that calling a function like here is no different than calling an arithmetic operator. So that's one of the ways that it's simple, and one of the ways in which people often might think it's confusing. Here they're defining factorial, and interestingly enough, their factorial function, they're defining it just to be the exclamation point, indicating to us that in this dialect, you are able to define a function as name as a symbol. And there are some notes here about places where it won't tolerate white space because they've cut some corners on the parsing here. And there's a copyright notice at the bottom here, but I believe the authors are these three right here, and hence jar being in the file name there. So congrats to you three over in Helsinki in 1989. And we're going to try to make some sense out of this right now. And lesson learned from the donut video, because 40 minutes in, someone actually noticed in the comments, and great eye, that I had made an off by 1 error in one of my refactoring steps. And so in the subsequent video testing a donut, I show how we could have wrapped a test suite for it in the beginning, and been able to catch that in the process. So we're gonna start with our test suite a lot earlier today, but first let me just let's run this. Let's see if we can get it running, see if we can get it building. I went ahead and set the CMake here to use the standard of C17, which is the latest C standard as of 2017. But obviously this was written in 1989. We'll see if we have any difficulty get this building in C17. So these are before even C90 and before C99, right? So we've got invalid pre-processing directives. So that's the first thing we want to do, is get this building. I've put the original one up in my refactoring challenges in the Craft vs. Cruft GitHub org. So you see it's 03, exercise 3 right here, and I'll be putting my solution in a branch named after this folder. And I'll try to commit as I go incrementally so you can see the steps as much as I can. Now, so it's saying invalid pre-processing directive, and unsurprisingly, right, because the pre-processing directives are D and A when they should be define and include. So it just saves space, right, because these are judged by number of characters too. They often are doing these very aggressive define macros, to the extent that the word define has been redefined. In a later version of C, they decided you can't do that. They don't like to break compatibility very often, but they definitely don't want people doing that. So I'm just going to do a little search and replace here. So we're going to look for D, and I'm going to actually make that a regex and put a word boundary there for a little safer search and replace. If we don't have the IDE support, we can at least do that. And get these defines being normal, and then include similar story. So we got those. Let's see, can we build now? We still got one build error. We're better, right? And then we can run this thing and try it out, right? Implicit library function exit. All right, so we definitely need to include something or other in order to have exit. So I'm just going to search for exit and see, you know, and it's gives me like a little man page that someone's pasted into some other website. But surely this will tell me, yeah, looks like it's in stdlib.h, and we've already got stdio, which we usually need. So let's see if we can build this thing now. I should mention a reason that I'm using the JetBrains IDEs is that they have very good refactoring support, and their refactoring support of Java is really a gold standard. In C, it's not as good, but it's better than you're going to find in other places, so I shouldn't have to do quite so much of the manual text search and replace kind of stuff I was doing on the donut video, though I think I will have to do some. So all right, we're running it, and it's just waiting for me to do something. So what if I type what I know to be a pretty normal expression in Lisp? It added 1 and 1, so that's cool. Let's try one of these examples from the Readme. Let's define this Fibonacci function. Not to worry about how the spacing is going to work. I'm just going to define this on one line. All right, we've got fib, so now can we call fib of 1, fib of 1,000 Fibonacci? All right, well, 1,000 Fibonacci knows is doubly recursive, right? So that's asking a lot. It's probably, I've overflowed the stack here. Let's try this again. Let's try with the factorial function here. All right. So can we do 5 factorial? All right, can we do 100 factorial? No, okay, we've overflowed again. So we've got some limitations, but nonetheless, this is working, I believe, as intended. So we go through some more examples here, but we've got now a working build. That's definitely a commit point. That's a cause for little mini celebration here. The CO is my alias. If you haven't set that up, you can't do it that way. It would be git checkout, right? And now we're going to do git commit. Let's see, message builds. So what I'm worried about now is as I start refactoring this that I'm going to break it. And with these Obfuscated C programs, these are incredibly easy to break because they kind of pride themselves on relying on really weird kinds of behavior that normally you'd be able to make assumptions on what would change. So I think that very quickly I'd like to get a test suite around this. So we can see in the Readme, you've already got some inputs and outputs that are expected. What do you say we just get that into a test suite? Now we could do this in C. I'm going to go ahead and use PiTest because that's what's just going to be easy for me right now. But we're going to do this in a data-driven way such that we'd be able to take those test cases and drop them into whatever runner you happen to prefer. So I'm going to make a little directory for my tests, and I'm going to start a pipenv environment here. We're initializing. All right. So now if I run Python, what's my version? 3.10. Great. That's a great version of Python. So then I'm going to want PiTest, I know. So we do pip install. We could do with just dev as a dev dependency if we also had ones that aren't, but because I'm just making a test suite, I'm not gonna bother to do that. So let's make PiTest, and I think golden file testing is the style we want to use. And I think that there's a plugin for PiTest, which I've never used before and I've kind of meant to use for golden file testing. So let's use that today. Let's learn about that. Actually, having looked a little more into it, that golden file package is really useful if you want to be able to easily run on update test after you've passed, changes to the golden file, that you want to propagate, but it's probably a little more complex than we need to do. I think just with parameterizing normal PiTest cases, we might be able to do what we're trying to do. So let's try and do it that way, a little more simply. So we can just mark a test as parameterized. We need to import PiTest, and looks like they've got a couple files they're going to pass in. In this case, they've got like 3 things they want to parameterize, but I just have input and output. So we want to do that, and we're going to get this from a file is why I'm doing this, so we don't have to find a new test case function for each. And we're going to need some test data, but in this case, let's just simplest thing. Let's start with, I know that I have one case where I want to pass in +1 and 1 like we just did in the console, and I know that the output I want from that is well, it would be 2, but really it's like that. So let's first let's see if this will run even without any assertions, and then we'll show how we're going to get this to run the executable. Okay. Function news is no argument. Yeah, we gotta. Good. All right. So that's expected, right? It didn't actually do anything. But now what we're going to want to do is get this to actually run the executable that we've built. So for now, I'm going to just say, it should run that. Let's see, from content root, from repository root. I don't know exactly where we're going to need to run it, but there is such a file here. We would probably want to build it to some other defined place here instead of cmake build debug, but little by little. So there is this path. We probably need to do something like this because we're running it from the test directory. We'd want our Readme to say exactly where you need to run this from, so it'll work. But let's say we need to run an exe from Python and capture the output, which is what we're going to need to do here. We're going to give it some input and capture the output. This allows us to put tests around this without making any changes to the code yet, because right now the code's very difficult to change. So we want to get some tests around it before even we have anything else. I've tried doing this in Bash as well, and that's certainly something you can do, but getting all the test output to be clean in Bash is sometimes very difficult. Okay. You win. I'm going to use the popen interface. Okay, bytes like object is required, not string. Okay, that's fine. So if we want to get a bytes like object out of a string in Python, does anyone remember how to do that? So can I just do that? No. Can I 2 bytes in Python. Encode. Okay, cool. We've got decode, we've got encode. That's kind of logical. Now, we're doing this as UTF-8. You know, who knows if we can actually give and receive UTF-8 from this particular process. It might be expecting ASCII. You know, maybe it won't matter in the cases we're going to look at, but that's a concern here. Offered object has no decode. Let's try that. Okay, so this is just hanging now, which means it's probably giving it, it's probably doing something good here. So we need to give it some input and then give it a new line, then an output, and then maybe we can send it an end of file character. So that would indicate like, okay, we're done, you know, get it to close. And if we can't close it that way, then maybe we can close it by sending a SIGINT or something. Python send EOF to SDD in close. We're calling our process RIS here for some reason. We should probably like something input stream, I don't know. So we'll do that. We'll get the input, put in the input, get the output, and then close the stream. That makes sense. And then we're going to do the comparison. So let's try it. All right, can't concat stir 2 bytes. Okay, well that's actually fair. Put the new line on and then turn it to bytes, right? Oh, I get it. We're saying read forever, and we need to, it's just the order that we're doing this in. We need to send the input and then that, and then the end of file character, and then start reading, because if we just say start reading and then, you know, it reads forever, we never get a chance to send our close. I think that's what's going on here. Beautiful. So after all that, we've got our feedback loop, right? So doesn't quite do it, probably because it's expecting an end of line here. So let's just see if let's just assume that there'll be an end of line at the end of the output we're expecting here. All right, beautiful. So now we can make our golden file here and put all these examples in there. So for that, I'd like to use some YAML. You may have something else you'd rather use. That's just fine. But we're going to use YAML right now. And so PiYaml, I think, is how a good default way of using YAML in Python. All right, excellent. So what's going on here? Unsupported operand types for plus, float, and stir. Oh, one of them's a float. That's not good. So we definitely want it to always see the output as a string. It would be nice to be able to make that something that we didn't have to remember in the file format, but for now. All right, great. So having done that, we can now specify a bunch of these, and we don't have to mess with this anymore. That's like the entirety of our test harness code, and then it's just data. So let's see what we've got back in our friend the Readme. These are all things that it supports, though we don't have the outputs, but we will. I'm seeing that some of these examples interrelate, so we'll get to that. Let's see what would happen if we were to do it like this, huh? We could give these cases names if we wanted to. You know, we'd be like, the name of this case is you know, whatever, as another element here if we wanted to make it a little more friendly. But I think it's okay like this. So let's see what happens if we run this. Okay, so unsupported operation types for plus none type and stir. Okay, well, we definitely don't want a none type in our comparison here. So it's trying to, I had left that blank, and so it's trying to add a new line to nothing, and Python choked on that is what happened, I think. All right, great. So in this first case, we've got a nice failure and saying it really outputted that. I think that is just fine. It's kind of silly that it puts all the extra zeros, but you know, it's very simplistic implementation. All right, so we got no output from this one. That's no good. What about these others? So I think we might be running into our issue where extra white space is becoming a problem. So let's just focus on one of these, get it working. Well, let's see what it actually does. Let's see how correct is that. So it should give me fib and then give 89. So is the problem that we're giving it spaces? Is it angry at the spaces? Could that be the results, the issue here? Yeah, it blows up if we give it spaces before the lines. So I'm thinking that could be the issue here. So we're joining them with space and then put one new line at the end and then close. How's that? All right, good. This is what I expect. So what about that? Is that now? Yes. All right, cool. So I think now we should be able to follow that pattern for all the rest of this, right? Can't believe it took that long just to get a workable testing harness here, but you know, it's going to pay off. And notice that I'm just gonna go ahead and do the put the new lines in line here, because I don't want to fidget with getting the trimming exactly right, but you know, we could imagine doing that in the test harness if we wanted to. So that should pass, and then we should have one more. Okay, it fails. Neat. Doesn't quite. This is not expecting that final new line. Cool. And one more. So we can say now that we've got a decent amount of confidence, maybe not certainty, maybe not proof, but we've got a reasonable confidence that as we change this, we're not modifying its behavior. And we know exactly what we would do if we wanted to increase that confidence, right? We would utilize more of these features and you know, put more cases in here. But this is a good starting point as far as being able to really say that yeah, we've got a good you know, level of confidence here. So for instance, if I were to break this, right? So let's just change any old thing. Well, we didn't rebuild it. It only works if we rebuild it. So the workflow is a little broken there. Yeah, bang. Huge pile of failures. None of the outputs are the same. So very quickly we'll be able to now determine if we've broken this, and be able to go back exactly to when it was right. So let's build this again. So, shall we begin to unfurl this? I think the next step here would be to take these pound defines off here. So what I'd like to do is be able to take these pound define macros and just start to inline them like we would do to inline functions, and just undo this this craziness of pound defines that this has wrought on us, right? So like we're pound defining return as u here. That's crazy. You should never pound define return. Some would say you shouldn't use the preprocessor macros at all, but you shouldn't use them most of the time. You definitely shouldn't pound define return as a capital U. So can I just say inline that? Unfortunately, I can't, because it's used in another macro definition. But once we get these out of use by macro definitions, we'll be able to actually use them more broadly. So, or we'll be able to do the full inline workflow. So that's cool. So let me just take this. First, we got a lowercase p. Let me just look at the other uses of that. They've got char star as that lowercase p there, there, and there. Cool. So now it's not used in macro anymore. Boom. We get it in the rest of the file. We've got this uppercase P. That's not used in a macro, so I think we should be able to inline that. The stir comp thing has got a pound define around it. I should be able to do an inline, yeah. All right, cool. Now this one, we've got one use of that in another macro. We'll do that one manually, and then the rest of it we should be able to, no more uses of that, awesome. And then W, not use another macro. This sberg thing, which I have a feeling is going to come to haunt us, because that is not something that is considered a good idea to use. So we can't inline that yet because it's using one other macro, but now we can. So A to F is Z over here and over here. Boom. This E is space is what that is being defined as. Can we inline that? Yes. And D, there's just one example of that being used in here. Cool. What about this E? Is S calling S on C of underscore? Great. And let's see if we got any other. Accidentally cut it instead of copied. That's not going to be good. Cool. Any other uses? No, I should be able to inline that. Excellent. We've got B of Y, and B of Y is B of Y over here too. So even though it's got an argument, I can paste this over. Otherwise, I'd have to replace, you know, what the Y is used for. And notice they've got actually a macro that includes an open paren but no close paren. That's really bizarre. So let's copy, not cut. There we go. Is there another B? No, just throw out the rest of the document. All right, so I can inline this now, maybe. Yes. And G is the last one. Great. So this would be a good commit point, except we don't know that we didn't break it. So let's build it. And then let's go in and run our tests. All right, we probably didn't break it. Macros. So having done this, we are now in a good position to format the file. When the preprocessor macros are mangling the syntax of the language so terribly, you can't really format it very well. But now we should be able to format it all right, and we can do this with IntelliJ, but I've had better luck with the clang formatter. So let's go ahead and do that. Clang format main.c, which just gives an output. And I can't do it over the top of main.c because that's the input of the command, but I can just use a little bashism to work around that. I can output it to a file and then move main.text to main.c. Normally IntelliJ's formatting will work just fine, but you know, on these crazier examples, clang format is nice. And you can actually have a couple of different, you know, right now it's set to GNU style in this clang format file I put in here earlier. GNU formatting is a little bit weird because, you know, for example, if we were to put in these optional braces, right, and then run the formatter, GNU formatting puts it halfway between, puts the braces like halfway between the statement and what's in it, which is weird. So in honor of friend Chelsea Troy, let's actually go to Mozilla style. And the default LLVM is also quite fine. So let's go back there. Okay, it's indenting a little more normally now. Now, that's a good commit point. Let's, very rare that a formatter would break it, but let's go ahead, let's make sure. It'd be nice to have a make workflow that did the build and ran the test in one step there. We might get to that. Cool. So let's commit as formatting. Now, the next thing I've noticed is that there's all these whiles and ifs and fors that are doing one-liners, which, like, you might think that's okay. You might think it's not in general. Consult your team's spec, your code standard. But in this case, we've got lots of cases where, you know, it's doing way too much in one line. We're using the comma operator. We're doing weird stuff. So I really would like all the optional braces after these statements to be there. So let me go ahead and do that. And you notice the IDE is going to be very helpful. Although it's putting them on one line, which I don't actually want, but that's okay. We'll undo that. Okay, add braces was 4. This if I'm just gonna add them everywhere we possibly can. Just kind of defensively in this case. Noticing we've got variables called underscore. That's not great. We'll probably want to get away from that for too long here. Okay, this one, it can't even, it's too convoluted. It can't even figure it out, but I'm going to do it for it here. IDE getting confused. I don't blame you. Cool. I think we got most of the optional ones in there. Let's do the formatting again. Good. So let's build and run PiTest. Excellent. So, where another good commit point? Optional braces. Now, are we anywhere closer to understanding this code? Well, not really. I don't understand the code any better, but we're starting to see, you know, comparing again from where we started over in here, right? From here, where they've spelled out obfuscated Lisp in the code cleverly here, to this, okay, we're starting to at least see, like, we've got structure, we've got functions, we've got loops. It seems like almost our understanding cannot indefinitely hide from us, even though it is, everything's named very, very obtusely. I'm, you know, beginning to see we're over a hump, not the only hump, but a hump. Something else that I'm noticing here is there's a very kind of antiquated notation, which probably just because this is made in 1989, of there's char star, the function return type, and then the function name and the function arg list, as you'd expect, and then the types of the arg list after. And that's very antiquated. We don't write C like that anymore. So can we, no, it's not letting us there's no auto fix for it, but that is going to bug me. So let's just go ahead and fix that up there. And we'll gain a few characters and some readability just off of doing that. So Okay, we have this function called z. It's not doing anything but returning itself. I don't know why you have a function that does that, but one thing at a time. This calls C of S of C. You know, what do any of those do? Who knows? We're gonna find out. Char star. Got lots of char stars here. This program just lives and breathes char stars. That's actually not very surprising at all. All right, so we got a char star I and a char star S coming in here. You know, maybe find out, and this is probably where one of those things that was spelling out Lisp came from, right? The L, the I, the S. Certainly they were not named, you know, to be good variable names. They were just named to spell that out in the code. Got a little B function here. I don't know about you, but I find this stuff relaxing, actually. Just little cleanup, but a little bit monotonous nonetheless. A function called G, you know, what's it doing? Built-in sprintf chunk, so some kind of output maybe. Got lots of variants of this. These all kind of look similar. And it's something, I think this flagged a warning as well. Like, you got a ternary operator, which is a conditional, an inline conditional, and if 2 is greater than 1, do 1. Otherwise, do 0. 2 is never greater than 1, right? So is that just a distraction? Like, does that do nothing at all? Probably. Interesting there. Interesting choice. I think that's probably just part of the obfuscation, you know? Okay, so I've touched this a lot. This is starting to make me nervous. Let me do a build. All right, we got some warnings, but we built okay. And run the tests again. Okay, we're good. And yeah, then we've got an inferred integer type on main. We should declare that. We should not make it implicit. All right, cool. So we've cleaned up the style of these guys here. Remove old style function arg types. Great. So as we scroll through these, like, where's a place we get some knowledge? Like, I see a bunch of gobbledygook as far as this. I see this main, which obviously we could start from main, start from the entry points. That's often a good thing to do. I also see these. This is meaningful, but what's really interesting is, like, this this not. We've got a warning here that this is unused. Could it be that this giant piece of code in this minified C was unused? Let's comment it out. Let's see what happens. Builds. On the test. Kaboom. Breaks everything. So really, we can just, like, uncomment this unreferenced variable and it'll really break it. We didn't break it earlier. Wow. That is messed up. Like, Commenting out an unreferenced variable should never break your program. But if we look at the warnings, we got a hint about why this might be, I think. Got main used in a recursive call. That's bad, but that's not the particular bad thing that I'm referring to here. Value never used. We know we cannot rely on that anymore. And what I'm referring to is this guy. This warning, that was flagging a warning earlier. I don't know why it's not flagging a warning now. Don't worry about it. But sberk. Let's learn what sberk is. Memory management system calls. Okay, so we're doing memory stuff. And basically, my understanding is they're called from higher level memory management library functions such as malloc, memory allocate, right? You generally use malloc, you use free in C. You don't go around using these lower level memory constructs like sberk. But we don't have a single malloc in this. We're doing this sberk stuff to like say, okay, I just want you to extend the amount of memory that I have, and I'm going to operate on my memory kind of willy-nilly rather than declaring these particular blocks I'm going to associate with particular variables. So I don't really understand how that is working, but I know that is something that is deeply evil and probably has to do with how we can put values in a non-existent, a non-referenced variable, and something else is referencing it by doing some memory unsafe thing. And what's interesting is like you'd think that would be like unspecified behavior, but apparently it's specified well enough that a program written in 1989 that relies on that still works today. So I guess it's like it's POSIX standard or whatever what they're doing, but still not a good thing, not a thing that you should go around doing. So this means we have some particularly brittle code, and maybe very hard to understand what's going on with this sberk stuff, and we cannot get rid of that. But look on the bright side, we found something, like, because there's text in this. We've got an if, and there's a function associated with if, and we've got equal, and there's a function associated with equal. These probably mean something related to these terms in Lisp. And if you don't know Lisp, char and cdr are meaningful there too. Char is the first element of a list. Cdr is the rest of the list. So if you wanted the second element, you're getting the first of the rest, the char of the cdr, sometimes called the catter. And a con cell is how you can create a linked list with from its first and rest. And then T is just true. And instead of false, we have nil, which I think in this dialect they're making is just expressed as open paren, close paren, like an empty list. So that's a source of meaning we have here. We know that this is not if, the F, cap F, right? This is something about if. Figure out what later, but something to do with if. And we could do the rest of these. We also know, like I mentioned, we've got the entry points. So from there we could figure out, you must be taking input, you must be parsing it somehow, then you must be evaluating it. I'm looking for a particular structure here. Let me tell you a little bit more about the structure I'm looking for in this. And the reason I know what structure to look for is because I know what Lisp Interpreters are supposed to look like. And Peter Norvig is a good person to read on this. But there's lots of people that have just talked about here's how you write a Lisp interpreter. Like SICP, the Structure Interpretation of Computer Programming by Hal Abelson and Sussman of Computer Programs, I think. And they go into a lot of depth, but there's a particular very short example, how to write a Lisp interpreter in Python, a very short one called Lispy. It's gonna highlight it a little better. And this is just like fairly complete Lisp, just like we just saw, or at least usable, serviceable Lisp. And it's just like in 145 lines, but very readable lines. And you can go look at this later if you want. But what I know, if I'm reading a Lisp interpreter, is that I'm likely to see a certain structure. And it's a REPL, right? That's what they call this, and that stands for read, eval, print, loop. It is a read, eval, print loop because it's going to read your input, it's going to evaluate it, it's going to print the result, and then it's going to loop, it's going to do it again. And that gives you this workflow that you can use the Lisp programming language with. So somewhere is my REPL. And within that, I'm expecting also certain structures. Open this back up here. I'm expecting that the eval is going to look for certain special forms and handle them in particular ways. Does this look like anything? Well, we just saw this big map of keywords to functions. So like, yeah, that's my eval. That's the things that are available on my environments. That the evaluator is going to use. And this is the eval. It's going to say, okay, if I've got a quote, I've got this handling. If I've got this handling, yeah. So this looks very familiar to me now. Even though, it's all quite unreadable. There's some structure in here I can extract out, and even though. This is a case where they've written something that there's already perfectly serviceable versions of. When you're dealing with legacy code, okay, yeah, this is a rules engine. This is a this is a parser. There are certain structures you start to realize. Okay, this ought to have these basic components. I just need to figure out where they are. So let's look at this. Something about if. So. SCA, we've got a stir comp of SC of something, okay. And then it's comparing that to, it's comparing SCN, whatever that is, to nothing, which is our empty list, which is its version of nil. You see down here we've got T and nil, nil and T down here, true and false, right? That's this Lisp dialect's way of saying false and true is empty and T. So if not stir comp of this processing of in we're going to do, if not stir comp of nil, and if you look up how stir comp works, it's string comparison. Here we've got even got a little man page on it. It will return 0 if they're equal. So not stir comp means if they're equal, right? You kind of have to mentally take out the not in your head. So if they're equal, if the input processed somehow is equal to nil, then we return a of in. Otherwise, we simply return in. Okay. So somehow that implements an if somehow, maybe? Interesting. I'm still not ready to unpack what that actually means, but we can start reasoning about it. So let's try coming in from the get-go here, right? The top level, the entry point. While is space k get cur blah. This is that EOF handling. We get that. we're going to exit, and then we're incrementing something. It's looking for parens in some particular way. But ultimately, what are we doing? We're getting input clearly here. Nothing else really could be happening. And then we're doing output. So this is our read. That's our print. And this main invocation, a little weird to do that with recursion, but that's our loop. So what else we got? S of O. That kind of must be an eval, right? So can we extract this? Read line, something like that. And you know, it's operating on globals now. That's not good. But at least now we know that segment is doing that. And then this must be the result. And this must be the input. And this must be an eval. So make sure I've done a lot of steps here. Ah, crap. Okay, I've broken something. Didn't like when I renamed them to eval. Was that all it was? Okay, well, we'll do that more carefully in just a second. Let me make sure that I've got green test still. Okay, good. So what I tried to do was rename this guy to eval. What's going on? Ah, conflicting types. Is it that something else is called eval? Change it to something else? No. Still conflicting types. Okay. So why are there conflicting types? Declared in main.c. And then there's an implicit declaration. I see. I don't know why that wasn't a problem when it was called, you know, why it was called S. But yeah, so because it's C, gotta, let's see. Oh, I see what's going on. They've got like several of these declarations on one line, and they got confused. So their refactoring support not perfect here. We'll just get that out of there. Then we got that declaration. All right. Good. And now we should be able to rename it what we like. RHS. Excellent. Great. And I mentioned before, it's a little weird to recurse into main. In fact, I think we got a warning about it. In order to do our looping, we could also have a stack overflow that way. So let's just do a while one, in the absence of while true, which I think we have to do an import for. Throw that in there. Notice we're recursing, like we've got our infinite loop. And then after that, there's this printf. Like I don't think we can ever get to that. So I think that was just a red herring. Like I don't think that was doing anything. All right, cool. We still got some warnings, but no errors. Test still green. All right. Great. So we got our read eval print loop, and I'm noticing this comma operator is showing up, like just for sequencing, doing some code golf to putting more than one thing on one line when they shouldn't be, and I see that a lot here, right? So can we just we can't do a quick fix on it, but I do think we should not be using these comma operators. So I'm just gonna get off on a little side quest here and undo those, unravel those. It'll be a little bit better. So we're looking for needless applications of the comma operator. That's one right there. We might not catch them all right away. That's fine. That's a separate line clearly. And again. All right, cool. So there's less of it now. There's one more. So all right, cool. So we didn't manage to break the code doing that. Neat. So if we just follow into the eval, what do we got? Well, we've got a very bad parameter name, which is underscore, but now it's input, so that's cool. We've got this li and this s, which surely was meant to spell Lisp in the obfuscated source code. Definitely not useful information there. And we're going to check if the input is a number or if it is nil. And if that's true, that just evaluates to itself, and it just returns the input. Well, that makes sense. What can we call that? And that really should be a bool, but there is no bool. Well, is there? Looks like you can import it from a standard bool. So let's go ahead and do that. To be a little more communicative. Where were we? We're in eval. And that if method we were in earlier just got a little more readable, huh? So if self-evaluating, return self. Great. Notice we're using a global here, right? Yeah. I don't like globals. I think that's the next thing. Let's see if we can get rid of these. So just make sure we're at a clean build point. We might be at a good commit point as well. Let's see what we got here. Yeah, get rid of the comma operators. So we saw y first, right? Let's look for y. I'm going to put word boundaries on either side of the regex so we can isolate in case we have longer names here. So what do we do here in C? This method C, we assign it. I actually got another case of some gratuitous comma operators, whatever. We'll get them when we get them. We assign it, then we use it twice. What's the other uses pattern? We're assigning it in the for loop, and then we use it a few times, right? Here we assign it, and then we use it twice, and we're reassigning it actually as well. So what's the pattern here? Like every time y is used, we're assigning it anew, and then we're using the result. So that means to me that like we really have a local variable masquerading as a global variable. So what was its type again? Oh, it doesn't say, which means that it's implicitly int in C, right? So that means we don't need that, right? Like, and it may actually be serving different purposes in different places. So int y equals 0. So let's declare it there instead of just referencing it and resetting it there. And let's do this every time that we see y. So let's start out with this increment of underscore, which is a terrible name. Then we set y. And then we do the rest of whatever we're doing. While we're at it, let's just rename that in, because we're passing it in. It's got to be called that. Makes sense. We find out more about what it is. We can rename it later. Okay, so let's see. Similarly here, so we can just declare that right in the for loop. Great. So now y is a local variable. We're down to still just warnings, and only 3 of them, oddly. Though if we turn on more, we could probably get more. Beautiful. Is that fresh build? Just make double sure. All right, cool. Remove global y. So that was pretty easy. You know, we just untangled a little bitty part of this. I wonder if we'll be able to do that with others. So what about k? So here we're assigning it, then we're using it. What I'm looking for is, do we ever use it without assigning it in that same block, right? Oh, this is actually just used in one place, so that's a no-brainer. So, and what we assign it, we only assigned one thing, which is get char. So it's really just ch for the character. We call it input char if we wanted to, but you see ch often as a naming convention for a character in C, and get char does return an int, so that's you know why it's an int. That's not actually that unusual. So cool. We've got another global. Remove global k. suppose we might as well run the tests. So what other globals do we have? Well, we're down to just a few. So we've got this M. Let's say we're using M. So we're using it as an array index here in this two-dimensional array called R. We're incrementing it. So there's a global variable, but we're incrementing it. So we're using it several places. It's being incremented. Like, it's non-trivial to make this not a global. And although I don't like that it's a global, that's going to be hard to do something about at the moment. But it's some kind of index. We know that much. What else? What else? So we've got this input, and we're also passing something called input to eval. That's probably not good. This global called input, we're assigning it, then we're using it and returning it. We're assigning it, then using it, then returning it. Then it's a param here, an eval. And hopefully it warned me, like if I was renaming this, hopefully it would have warned me if I were using that anywhere within it. Then we're evaling that. Then we're assigning it. Okay. So given that we run readline and then use it here, I wonder if really we don't need this as a global. So let's just experiment. We're on a fresh commit. We might have to undo this, but let's follow the commit errors. Right? And it was a char star. So let's say here we're declaring it, and again here we have this weird comma operator thing going on again. So let's unfurl that. And then just use it there. Get rid of one of these commas. And then they're assigning it again. It's fine, whatever. Where else is this used then? So we could just declare it here. And that needs it, right? But we can return it. So instead of setting the global state as the result this has, we can have a declared output. What's gone wrong here? Oh yeah, conflicting types. Okay, we'll deal with that. Then something's gone wrong here too. So readline returns a char star now. And then we're going to use char star input. We're going to declare it there and get it out of there. But then what's wrong with that? Let's build it and see. Oh, right. Semicolon. I'm sure you noticed that, some of you. All right, one error. Generate again, semicolon. Been in JavaScript and Python a lot, I guess. Though I like to include the optional ones in JavaScript. So All right, cool. Still runs. So we've eliminated another global. And then there's this H. What's that? So we assign it, then we, use it various ways, increment it in this loop. This loop, which is called Q, in this function called Q. We assign it, then we use it. We assign it here, don't immediately use it, but then we assign it in a read line. So I'm a little more speculative on this one, but it sounded like this doesn't really need to be a global. So let me try just declaring it everywhere it's used. We can roll back to the commit if this turns out not to pay off. Now, this, I think there's probably a relationship between, well, oh, I think we're just nulling it out because we're done using it. I don't think it's actually needed here. Let's really discard that. Test pass. All right. Weird that they would have had a whole line they didn't need because they're very, they were very saving a lot of characters when they made that. I wonder what that was about. So, great. We just got rid of another global. So when we got on this trip, we were decoding this eval function. So we got a little ways in there. So it's starting y at whatever some index is. We saw that earlier. And then it's decrementing, so it's going downward, and it's looking for something in this array of things, and if one of them are equal, then it's going to return the function that it needs to run, or it's going to return something. I'm still not quite understanding why some of these are in this one and some of these are in this one. And incidentally, like, the size of this array is way off. Like, there are not 99 of these. So this is all very confusing to me. But it's memory that's using for other purposes, I guess. Oh well. Back to the eval. Oh, okay. So these are also self-evaluating, I guess. That could be. So, anyways, if this doesn't happen, if whatever that is doesn't happen, then we evaluate C of input, comma operator. All right. And we store that in U, So we're evaluating some processing of the input, and then we're evaluating this other processing of the input, or not evaluating it yet, but we're doing some other processing of it. We might have to jump down that rabbit hole. And if u minus c, which I guess means if we're taking one character and we're subtracting paren from it, then that would mean that we would get 0 if the thing were already paren and not 0, in other words, a true value in all other cases. So I think this is the equivalent of is not paren. It's just a weird way of writing it. If is not open paren, then it's casting u to a function and calling it. And notice we're, in some cases, returning what must be a function value from this. Okay. That makes some sense. I don't know if it makes sense to you, but what I'm thinking here is that this, in the ones column, right? The zeros second subscript here is a name, and then the ones is a function associated with it. So going back to where we were, we're saying that we're going to call that value, that function, on the input. Okay. So what are these and what are these? Because these are keywords and these are keywords, but are they different kinds of keywords? There's a concept in Lisp called a special form. Maybe these are special forms and maybe they're not, but I'm gonna do my best to try and say that's what we're doing. So we can have some better word coming out of these than are. It's starting to have some level of meaning, though. Manage your expectations. So we're going to assign these to some index. We're going to check if not strcomp. So that's if it is non-equal, if input is non-equal to null, then we're going to set our memory out in space somewhere to the evaluated result of C of input, and then set this to blank, presumably to deal with it somehow later, and then set input to A of input. Okay, we're going to need to know, we've ignored this C of input too long. What is this? Okay. Well, first thing is it calls Q of input. Great. Big help. So rename the input again. So we're gonna, while it's space, we're going to increment our input pointer. So null terminated string array, right? And we've got this, maybe that's an index. Probably it's an index, right? We're gonna go forward while we've got spaces, so we're consuming all the spaces, then we're assigning H to input. So let's just say just got a marker, say, well, V, which it's not when it's 0, or is space marker, or is close paren, or is marker open paren and marker in. Okay, that's confusing. We're doing some paren parsing, and then we're incrementing this based on marker equals that or marker equals that. Okay. So I suspect what's happening is we're consuming like an expression, and it's doing paren counting because we need to know when we've closed as many parens as we've opened. So I think if we untangled all these, that's probably what would be happening. So what if this is equal to that, then that's a that's 1 for true, and then this would be false. So that would mean we're going 1 level deep, and this is 1 if that's equal, and that wouldn't be. So then we're going -1. Yeah. So this is going to subtract 1 if we're popping out and add 1 if we're popping in, basically. So I'm not describing that very well, but you get what's going on, right? We're doing paren count. So I think we can just say, we can more readably say, and then prove that this works by running the tests. If marker, then V++. Else if V minus minus. All right, so is that true? Does this work? Yeah. All right, so now we know what this is, right? It's not V. It's nesting depth. All right. So, well, nesting depth, or, so that's, in other words, well, nesting depth not equals 0. That's what that means, because it's coercing an int to a bool. And not is space marker, or is space. Okay, so I'm still having trouble with what is this, but it's something. So at the end of the day, what's it returning? It's returning the difference between the end of the first expression, because it's counting this depth, and then the beginning of it. So given that that's what it's returning a count because it's doing the implicit int type. So I think this is length of next expression. And I would sit here with like some truth tables and try to get more out of like just figuring out this one line. But right now my head hurts. I want to move on. I think that we would be able to figure out exactly what every bit of that meant. But I think ultimately what's going on is it's counting the nesting depth, and it is going to return how far it gets in evaluating. So I think this is the length of the next expression, such that if you had some spaces and then open, some stuff, close, it would say, okay, that's the end of the next expression, and then it would return this this length, this distance, which would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That is what I think this is doing, and we would be able, certainly, if we had some C unit testing going on, be able to test it directly and get that assurance that that's how this were behaving. But I think we've basically solved the riddle, even though we don't really know how it's doing it yet. Okay, great. So that was quite a long diversion. But this is used in a few different places, and so I think that this is going to be pretty useful to us. So now we're back over in C. I'm going to have to check out pretty soon. I'm going to have to defer more of this to the next iteration. We've got this string copy, built-in string copy check. What is that? Some internal stuff you're not supposed to use, probably. But it's probably doing a copy, right? It's probably doing a string copy. And stir end copy is the length bounded version of stir copy. So we're giving it this memory address that we're doing it with our eval sberk, and then an input, and then a count. Okay. Expression length. And then built-in object size. And then this is just, we've established before, 2 greater than 1 is always 1. So, or is always true. So this can just be 1. One would hope. Like, this is such a wonky program that I'm going to run the test anyway. And then input of expression length we're going to set to 0, which that actually makes some sense because that's a null terminator is what we're adding there. So we're at the end of that expression we're going to set a null terminator so that we won't traverse off the edge of that anymore. Unfortunately, we cannot read the documentation of this, and we'd probably do it if we went and looked at the GCC source code or some crazy thing like that. Oh, yeah, we got the comma operator again. So I was trying to read that all like it was one call, right? triumphs of unreadability. So I don't normally write these comments play by play what a method is doing, but increment in get length of next expression. Then we copy the next expression to memory somewhere, maybe. And then we add a null terminator to input after expression. And then we return that copy. So there's really, we're not returning the input anymore. We're returning our copy. I see. That's why we're not, that's why we're not adding the null terminator to the input. So this is a repurposed variable, which is bad. So that's really out from this point on. Yeah, all right. Now this makes sense. All that. Yeah, no, just only code uses is fine. All right, cool. Spelled right? Impression. It's not spelled that way. All right. Now what were we doing? But no, this is used all over the place. We struck a gold mine there. So if we go into our eval, right? Yeah. Then U is eval of the next expression. Okay, cool. Then U is, let's just declare where it's used. Value of next expression, maybe. Okay. And then A. What is A? We get so lucky that we'd be able to figure A out too. Go back to in. We're incrementing it. We're getting the length of the next expression again. We're consuming as much white space as we can find. Then we're allocating, that's not really input anymore. This is output in this case. We start output equaling paren, and then we copy this into it. So there must have been like a close paren in it somewhere, maybe. Interesting. So we're consuming space and adding an open paren. Yeah, maybe we're not so lucky that this is going to make sense. So literally like trim space and add open paren. Maybe. As far as we figured out. Okay. Whatever. Running the test. So we're doing something with this open paren. Getting a special form handler, setting some area to empty to maybe be able to use it later. We're resetting input yet again. Trim space and add open paren, and this is in a while. So I guess we're probably evaluating every expression. Yeah, evaluating every expression, getting them all into a buffer while not nil. I'm gonna extract a method here. Is not nil, so I can stop reading this not and not knowing what's going on. Now I can not know what's going on because there's a bunch of places this is used. It's just kind of confusing. All right, so we didn't quite do that right, did we? All right. It was 2 knots, right? Yeah. So, oh, okay, maybe I replaced it here. Maybe I accidentally made a recursive call. It's a silly mistake. So, great. Well, is not nil input. We're going to go through there. We're going to get the next expression. Well, it's not nil input. I'll take the special form handlers and we're incrementing this other index. I'm tempted to name it some other index. We got another bogus comma operator here. Okay, so this is still a little bit opaque to me. What's going on? It looks like we're assigning this sum index though. Well, I was going to say we're assigning it just to return, so we don't need it, but it's global. It's so that actually is an evil thing that we must preserve, and then we don't know what li or s are. But generally, I would say our evaluator is, this is getting dangerously close to lucid. It's starting to communicate a little bit about what's going on, and I think we're getting close to something. So I'm going to wrap it up for this first installment. So as you can see, it's quite difficult to take on these Obfuscated C contest winners, but as Lao Tzu said in the Tao Te Ching, with patience, the most tangled cord may be undone. And we'll be back to this tangled cord later. Thank you.